So, uh, every time you use Google or maybe Apple or Facebook to log into a local city app.
Right, like paying a parking ticket or something.
Exactly. Checking a bus schedule or maybe requesting a municipal permit, you are basically taking your private civic life and handing it directly over to an advertising algorithm.
Yeah, you are quite literally paying for convenience with your personal autonomy.
And we do it every single day, right? Without even blinking.
Oh, absolutely. I mean, it has become the default mechanism for just existing in the modern world. We traded the physical wallet for the digital login, and in doing so, we unwittingly signed away our right to digital privacy.
And that is exactly what we are dismantling today. So welcome to another deep dive. Today, we are exploring some truly cutting-edge research projects developed by the Applied Computing Research Group.
Right, known as the GCA.
Yes, the GCA. We are going to unpack this brilliant, super timely 2026 paper titled Self-Sovereign Digital Identity System for Smart Cities, a pilot project with Trustchain and Hyperledger Indy, the Municipality of Santa Rosa. And I want to make sure we highlight and give proper credit to the authors right at the top because the work they are doing is just phenomenal.
It really is.
So this study was authored by Carla O. Castaño, Marcelo P. Chekin, Sandro Sawicki, and Rafael Z. France. And they are researchers operating out of Uniju University and URI University down in Brazil.
It is a remarkable piece of research, mostly because it doesn't just, theorize about our loss of privacy.
Yeah.
It actually proposes a highly technical, mathematically sound, and rigorously tested escape route.
Which is why our mission for this deep dive is so critical for you listening. We're going to examine how our modern smart cities have kind of backed us into this corner, forcing us to trade our personal data for basic civic access.
Right.
And then we're going to look at the revolutionary concept these researchers actually tested in a real Brazilian city, a concept called self-sovereign identity.
Which is a bit of a mouthful, but we'll break it down.
Oh, well. We're going to explore how this technology might be the ultimate key to taking our digital lives and our private secrets back from big tech. So, to start, we really have to look at the environment that makes this necessary. The researchers anchor their work in the context of the smart city.
Yeah.
Now, that term gets thrown around a lot in corporate marketing. But what are we actually talking about when we say smart city in the context of this data problem?
Well, in the context of this research, a smart city isn't just, a place with good public Wi-Fi. It's an urban environment where everyday processes, governance, transportation, security protocols, the healthcare system, the energy grid, they are heavily automated and monitored in real time.
Okay.
And the engine driving all of this is the Internet of Things, or the IoT.
Right, but let's define the scale of that IoT. It's
Mhm.
not just a smart thermostat in your living room, is it?
Yeah. No, not at all. The researchers emphasize that the IoT infrastructure in a smart city is a massive, incredibly dense, interwoven web. We are talking about thousands of environmental sensors on light poles,
Wow.
industrial machines communicating with traffic grids, complex software platforms analyzing water flow, and of course, individual citizens moving through this space with their mobile devices. The IoT basically acts as the neurological bridge between the physical concrete and steel of the city and the digital analytical world.
And on paper, that sounds utopian, right?
Right.
The connectivity gives you, the citizen, access to an incredible range of frictionless services.
Oh, definitely.
Like if you want to know exactly when the next bus is arriving, the smart city tells you because the bus is actively pinging the grid.
Mm-hmm.
If a street light goes out, nobody has to call it, and the light itself notifies maintenance.
It's all about efficiency.
Right. But here is the friction point that the GCA researchers highlight. To interact with these amazing, futuristic digital services, you have to prove that you are a valid citizen. You have to authenticate to
You
yourself.
have to log in.
Exactly. You have to log in.
And historically, municipal governments have really only offered two deeply flawed ways to handle that authentication. The first option is that the local authority builds its own centralized data silo.
Right, the local honeypot.
Exactly. You go to the city's website, you create an account, you hand over your full legal name, your physical address, your email, your phone number, maybe even your social security number, and you create a password. The city then stores all of that in their local server racks.
Which is a nightmare for a couple of reasons. First, from a user perspective,
Mhm.
it's just another password to forget.
True.
But more importantly, from a security perspective, you have now created that massive honeypot. A local city government's IT department is suddenly responsible for guarding the deeply sensitive personal data of hundreds of thousands of people against global, state-sponsored hacking syndicates.
Yeah, and it's an unfair and frankly unsafe expectation. Centralized databases are structurally vulnerable. It creates a single point of failure. If a malicious actor breaches that one city server, they don't just compromise your parking ticket history, they compromise the identity data of the entire population in one single strike.
Right. So to solve both the security burden on the city and the convenience burden on the citizen, we move to the second option. The paper refers to this as federated authentication.
Right.
This is the ubiquitous log in with Google or Apple or Facebook button that has basically taken over the internet.
Exactly. Instead of the city verifying who you are, you use a massive third-party identity provider to vouch for you. The city's system essentially asks Google, hey, is this person who they say they are? And Google sends back a digital token saying, yes, we verify this user.
Wait, so by trying to avoid local government databases getting hacked, we just handed the master keys of our civic lives to massive multinational advertising firms.
We did. We absolutely did. And the paper is exceptionally explicit about the dangers of this. When you use federated authentication, you are essentially trading a structural security vulnerability for a behavioral surveillance vulnerability.
So,
Yeah. The researchers point out that the fundamental lack of user control in this dynamic allows big tech to exploit your interactions. They use your login metadata to generate incredibly deep, intrusive insights into your consumption habits, your leisure preferences, your health, and even your political leanings.
because the authentication isn't a one-way mirror. Like if I use Google to log into the city's public health portal to schedule a flu shot, the city gets my verification, but Google gets the timestamp and the metadata that I'm interacting with a health clinic.
Precisely. If we trace the mechanics of that interaction, every time you click that button, a digital handshake occurs between the service provider and the tech giant. You are actively creating a persistent data trail.
A trail that links your supposedly private civic life directly to your commercial advertising profile.
Right. You are telling a corporation that makes its money selling targeted ads exactly when you pay your property taxes, when you visit the municipal clinic, or how often you tap your phone to use public transit.
It is absolute madness when you put it like that. I mean, using big tech to log into your city services is like walking up to the bouncer at a nightclub, and instead of just showing him the date of birth on your driver's license,
Give him the whole wallet.
worse.
Yeah.
You hand him a complete unredacted copy of your diary, your bank statements, and your voting record, just so he can verify you're over 21.
That's a great analogy.
And he gets to keep a copy of it, read it, and sell summaries of it to the highest bidder. It's a massive, unnecessary overshare of data.
It is an incredibly dangerous overshare. And it brings us to the core structural problem with both of these older models, both the city-run honeypot and the big tech federated login. They are both centralized.
Right.
Even if Google's security is vastly better than a local municipality's, the fundamental flaw remains. You, the individual, have absolutely zero control over how your identity is managed. You have no say in how securely their database is maintained, who has access to it internally, or what algorithms are parsing your digital movements. If Google decides to shut down your account for a terms of service violation, you are suddenly locked out of your own city's digital infrastructure.
Which is terrifying. I mean, if my email provider decides I violated some opaque policy, I shouldn't lose the ability to pay my water bill or access my property deeds.
Exactly.
So the GCA researchers recognize this paradox. We desperately want the convenience and efficiency of the smart city, but we absolutely cannot accept the big tech surveillance state or the centralized honeypot risks that currently come with it.
Right, something has to give.
And the entire paper is focused on shifting control back to the individual. To understand how they do that, we have to pull apart two concepts that are central to the study: decentralized identity and self-sovereign identity.
Yes.
Now, they sound like synonyms, but they are not, right?
No, they are fundamentally different, and the distinction is really vital to understanding the architecture of the future here. Let's start with decentralized identity. According to the research, this is primarily a technical architecture.
Okay.
It's a system design where the storage and the management of identities are distributed across multiple independent actors or nodes on a network. The defining characteristic is the removal of a single central authority.
Okay, let me make sure I'm following. If a centralized identity is like keeping all of your money in one giant mega bank downtown, or one vault breach ruins everyone.
Right.
A decentralized identity is like moving your money into a massive network of thousands of smaller, interconnected local credit unions. the risk is spread out. There is no central vault.
That is a very solid way to visualize the architecture, but here is the critical nuance that the researchers highlight, specifically drawing on the work of Muehl and his colleagues.
Okay.
While that distributed, decentralized technical architecture is a necessary foundation, it does not actually guarantee you total autonomy over your identity.
Wait, why not? If it's spread out, no one is in charge, right?
Well, not necessarily. Some decentralized identity systems still require intermediaries, or they operate under strict governance constraints imposed by a consortium that set up the network.
Oh, I see.
To use your analogy, you might not be relying on one giant megabank downtown, but the board of directors for that network of local credit unions can still freeze your account, change the rules, or monitor your transactions without your explicit consent. The database is distributed, but the authority is still partially abstracted away from the user.
Ah, okay. So I'm no longer dealing with the mega bank, but I'm still asking for permission to use my own money.
Exactly. And that is where we enter self-sovereign identity, or SSI.
SSI, got it.
Self-sovereign identity goes far beyond the technological architecture. It encompasses what the paper explicitly calls normative principles.
Normative principle.
Yes. SSI is a philosophical stance literally baked directly into the cryptographic code that dictates the individual user must be the absolute, primary, and final authority over their personal data.
So every self-sovereign identity system must run on a decentralized architecture, but not every decentralized architecture is truly self-sovereign.
Precisely. If decentralized identity is the network of credit unions, self-sovereign identity is like keeping your money in an invisible, mathematically unbreakable vault that only your specific biometric and cryptographic signature can open.
Wow.
And you carry the only key with you wherever you go. No board of directors can freeze it, no tech company can monitor it, and no city government can revoke it without your explicit cryptographic consent.
That sounds incredibly empowering, but how does it actually work for me, the citizen, on a daily basis? I mean, if I don't have an account with a city and I'm not using Google, what exactly am I using to prove who I am?
Well, the mechanics rely on two specific technical components detailed in the research. Decentralized identifiers, which are called DIDs, and verifiable credentials known as VCs.
Okay, DIDs and VCs.
Right. In an SSI model, instead of logging into a database, you hold these verifiable credentials inside a secure digital wallet application on your own device. You can think of a VC as a digitally signed, tamper-proof claim about some aspect of your identity.
Like a digital passport card.
Similar, but much more granular. So one verifiable credential might simply state, this specific identifier belongs to a verified resident of the Municipality of Santa Rosa, and that claim is mathematically signed by the city government's private key.
Okay.
A completely separate, verifiable credential might state, this individual is over the age of 18, signed by the federal government or a trusted banking institution.
And crucially, these credentials live on my phone. They are stored locally in my wallet. They are not resting on an Amazon Web Services server somewhere, and they aren't in a filing cabinet at City Hall. I hold them.
You hold them and you control them. But the true genius of this system, the mechanism that makes SSI so revolutionary, is how you present those credentials.
What do you mean?
You never actually hand over the credential itself to a service provider. Instead, you use a complex cryptographic process to prove that the claim within the credential is true without revealing the underlying data. This is called selective disclosure.
I really want to dig into selective disclosure because when I was reading the source material, this felt like magic.
It really does.
It feels like the ultimate superpower for digital privacy. How do you prove something is true without actually showing the proof?
It relies on advanced cryptography, specifically mechanisms related to zero-knowledge proofs. Let's look at a practical example.
Please.
Suppose you want to purchase a restricted item or access a city service that requires you to be over the age of 18. In the physical world, or in a centralized digital world, you have to present your driver's license.
Right, which means the person checking my ID instantly learns my exact date of birth, my full legal name, my home address, my height, my eye color, and my organ donor status.
Yeah.
All just to prove I'm older than 18.
Exactly. It's a massive data leak. But with selective disclosure in an SSI system, your digital wallet reads a credential that proves your birth date. It then generates a mathematical cryptographic proof, a complex string of numbers that definitively states the math confirms this user fulfills the condition of being over 18.
Just the math.
Just the math. It sends only that mathematical proof to the merchant or the city service.
So the system on the other end just gets a cryptographic yes or no.
Precisely. The verifier system checks the math. If the math holds up, they know with absolute certainty you are of age. But they learn absolutely nothing else about you. They don't know your birthday, they don't know your name, and they don't know where you live.
That is staggering.
You only disclose the exact sliver of data required for the transaction, and the cryptography ensures that sliver is universally trusted.
Let's take the nightclub bouncer analogy from earlier.
Sure.
Selective disclosure is like walking up to that bouncer, and instead of handing him a card covered in your personal information, you hand him a completely blank piece of plastic.
Hey.
And because of the cryptographic math, that blank piece of plastic just glows green. The bouncer knows, mathematically, that a trusted authority verified you're 21. But he doesn't know your name, he doesn't know your birthday, he has nothing to write down, and he has no data to sell.
Exactly. It completely inverts the power dynamic of the internet. You navigate the web and your physical city with a digital wallet where you are the sole sovereign issuer of your personal facts. You decide who sees what for exactly how long, and you leave no exploitable data trail behind.
Okay, so the theory is flawless. But cryptographic theory on a whiteboard is one thing, right? Deploying it so a busy parent rushing to catch a smart city bus can actually use it is another challenge entirely.
It's a whole other beast.
And that brings us to the core of the GCA's research. They didn't just publish a theoretical white paper. They put muddy boots on the ground, they built this architecture, and they tested it on real citizens.
Yes, the practical application is what makes the study so valuable. They deployed this pilot project in the municipality of Santa Rosa, located in the state of Rio Grande do Sul in Brazil. Okay.
They needed a real-world scenario to test whether this grand privacy-preserving cryptographic architecture could actually function in daily urban life.
And the scenario they chose to test this with was giving citizens secure, controlled access to an environmental data repository.
Correct. The city has urban sensors deployed throughout its infrastructure. Specifically, the paper notes the use of LoRaWAN IoT sensors.
Okay, let's pause there. What is a LoRaWAN sensor? I mean, why wouldn't a city just use Wi-Fi or Bluetooth for their smart city tech?
Good question. LoRaWAN stands for Long Range Wide Area Network. It is a specific type of radio protocol designed for the Internet of Things.
Okay.
If you are a city planner, you don't want to rely on Wi-Fi because the range is too short and it consumes massive amounts of power. You'd be changing batteries on 1,000 street corner sensors every month.
Oh yeah, that makes sense.
LoRaWAN allows battery-operated sensors to transmit small packets of data over very long distances, miles, even in dense urban environments using very little power. A single sensor can run for years. Oh, wow. So Santa Rosa has these sensors all over the city, tracking things like temperature, relative humidity, sunlight levels, and other environmental metrics.
Right.
And the researchers built a mobile app for the citizens. If a citizen wants to query this database and see the environmental data for their neighborhood, they open the app. But instead of logging in with Google, the app requires them to present those verifiable credentials using self-sovereign identity.
Exactly.
The paper states their goals were to ensure secure access, preserve citizen privacy, adhere to self-sovereignty principles, and increase the resilience of the city's overall IT system.
But I have to push back here. I have to play devil's advocate.
Please do. What's the concern?
My concern is the stakes. Why are we using environmental data for this pilot? I mean, if a malicious state-sponsored hacker breaches my SSI wallet or bypasses the API and discovers that I was checking the local humidity in the park.
Who cares? Right. Who cares? It's basically public weather data. It feels like using a 10-ton laser-guarded bank vault to protect a grocery list. By testing it on something with zero stakes, how do the researchers actually know this highly complex cryptography will hold up when the payload is actually valuable, like tax records or medical history?
That is a very common and very understandable critique of pilot programs, but it stems from a misunderstanding of how software engineering, specifically cryptographic systems engineering, actually works.
Okay, how so?
When you are building foundational infrastructure, the payload is initially irrelevant. The goal of this pilot is not to protect the weather report. The goal is to prove that the plumbing works.
The plumbing. Okay, explain that.
Integrating a self-sovereign identity system is not like installing a new app. It requires building a completely new, mathematically complex communication pathway between the user's mobile device, the city's application servers, and an underlying decentralized blockchain ledger.
Right.
It requires multiple distinct systems to perform cryptographic handshakes in milliseconds. If you begin your testing phase using highly sensitive data, let's say municipal tax records, and there is a single unforeseen bug in how the mobile wallet formats the zero-knowledge proof, you don't just get a software error.
You get a massive breach.
You get a catastrophic front-page privacy breach. Citizens' financial data is leaked, and trust in the system is destroyed before it even launches.
So it's about isolating variables. You remove the data risk so you can stress test the mechanical risk.
Precisely. By using environmental data, they create a low-risk sandbox. They are testing the entire complex authentication flow, the app generating the credential presentation, the server performing the cryptographic verification, the execution of selective disclosure, and the final data retrieval.
Right.
If the decentralized infrastructure can seamlessly, securely, and rapidly handle a citizen requesting humidity data without routing through a centralized server, then that exact same pipeline, the plumbing, is proven.
Because the math is the same.
Exactly. A cryptographic algorithm like AES 256 or elliptic curve cryptography doesn't care if it is encrypting a weather report or a nuclear launch code. The math works exactly the same way. Once the plumbing is proven in the sandbox, you can pipe highly sensitive healthcare or financial data through it with mathematical confidence.
That makes total sense. It is like an engineering firm testing a brand new, radically designed suspension bridge. You don't test it on day one by driving school buses full of children across it.
No, you don't.
You test it by driving fleets of empty, automated concrete trucks. The load on the structural cables is exactly the same. You stress the system to its absolute limits. But if a cable snaps during the test, nobody gets hurt.
That is an excellent analogy. The environmental data is the fleet of empty concrete trucks.
So if we visualize this from the citizen's perspective, you're holding this app in your hand in Santa Rosa. It looks like a completely normal, perhaps even slightly boring city services app.
Yeah, very unassuming.
But beneath the glass of your screen, it is seamlessly connecting you to the physical infrastructure of your city. The actual physical temperature sensors on the street corner, using military-grade cryptography. And it is completely bypassing the massive corporate tech monopolies that usually sit in between you and your city.
It is a profound shift in digital architecture. But to make that connection happen, to build that plumbing, the researchers needed an engine. They needed a decentralized ledger to anchor the cryptographic keys that make the identities verifiable.
Right.
And this is where the research gets incredibly interesting because rather than just picking one engine and hoping for the best, the GCA researchers decided to run a tech bake-off.
Yes. They implemented the entire system using two vastly different decentralized engines in parallel to see which performed better and to expose the philosophical trade-offs of each. Let's look at the contenders.
Let's do it.
Contender number one is called Hyperledger Indy. According to the source material, this is a platform maintained by the Linux Foundation. It is open source, which is great, but crucially, it is designed as a permissioned blockchain, specifically built for managing decentralized identity.
The term permissioned is the defining characteristic here. When we think of blockchains like Bitcoin, anyone with a computer can download the software, join the network, and start verifying transactions. That is a permissionless public system.
Right.
Hyperledger Indy is the opposite. It is a closed loop. Not just anyone can join the network and act as a node. The nodes that verify the cryptographic proofs are operated by known, vetted, and trusted entities.
Who decides who is trusted?
Usually a governing consortium. In a municipal context, the nodes might be operated by different departments within the city government, partnered universities, trusted local NGOs, and perhaps audited financial institutions. It is a decentralized network, but the participants are tightly controlled.
Okay, keep that in mind, because contender number two takes a wildly different approach. The researchers also built the system using a framework called Trustchain.
Right.
Trustchain was developed by the Alan Turing Institute over in the UK. And it completely rejects the permission model. It uses a public blockchain strategy. It relies on a decentralized public key infrastructure, or DPKI.
Let's clarify what a DPKI is, because it's vital. A public key infrastructure is essentially a directory that links public cryptographic keys to specific entities. Think of it like a phone book for digital identities.
Okay.
Historically, a central authority, like a certificate authority, owns and manages that phone book. A DPKI takes that phone book and distributes it across a blockchain, meaning no single corporation or government owns the directory.
And the blockchain that Trustchain uses to secure this phone book is the wild part. It doesn't use a specialized closed-loop network like Indy. It anchors its data directly into the global Bitcoin network using a secondary layer called ION, the Identity Overlay Network.
This is a fundamental philosophical and architectural clash. The researchers are pitting a permissioned, purpose-built, highly controlled ledger against a system that leverages the ultimate chaotic, permissionless, universally public ledger of Bitcoin.
So the GCA team set both of these up to see what would happen. And the very first metric they compared was just the sheer complexity of deployment. What does this actually mean for the human beings, the city's IT department, who are tasked with building this?
It's not easy, I'll tell you that.
Well, the paper is pretty blunt. Both are incredibly tough. They both require a high degree of specialized technical complexity. Setting up Hyperledger Indy requires deep knowledge of containers, Genesis files, and complex wallet management.
We should unpack those terms slightly so listeners understand the hurdle.
Yeah, please.
When the paper mentions containers, it's referring to software virtualization tools like Docker. Think of a container like a standardized shipping container for software. If you want to build a complex application, the underlying operating system of the server can cause conflicts.
Right.
A container packages the application and all its dependencies into a perfect, isolated box that will run identically on any machine, anywhere. It's efficient, but it requires specialized DevOps engineering skills to orchestrate.
And what is a Genesis file?
Every blockchain has to start somewhere. The Genesis file is essentially the Big Bang document of a new blockchain. It is the hard-coded configuration file that defines the very first block in the chain, establishes the initial rules, and defines the initial trusted nodes for a permission system like Indy.
Oh, I see.
If you configure the Genesis file incorrectly, the entire network is structurally flawed from second one.
Okay, so building Indy requires a team of highly skilled engineers who understand containers and Genesis files. But the paper notes that for an expert operating in a controlled environment, spinning up the Indy network takes about 2 to 6 hours. Which honestly sounds pretty reasonable for setting up a citywide identity infrastructure.
It is highly efficient. Because it is permissioned, the scope of the network is limited and manageable.
But then you look at Trustchain. Setting up Trustchain requires running a network node, deeply understanding its complex data anchoring model, and fully synchronizing the network. The researchers ran this on a Bitcoin test network called testnet3, and the synchronization process took 3 to 4 days.
Yes, it did.
Wait, 3 to 4 days just to turn it on? Why on earth does it take that long?
Because of the foundational nature of a public blockchain. When you spin up a full node on a network anchored to Bitcoin, you cannot just trust a central authority to tell you the current state of the ledger.
Because there is no central authority.
Exactly. To achieve total trustless decentralization, your node has to literally download and independently mathematically verify every single transaction that has occurred on that chain since the Genesis block. It is downloading the entire history of the ledger to ensure that no one, anywhere, has ever cheated the math. That computation takes days.
It sounds like setting up Indy is like building a very complex, advanced Lego set. It comes with a thick instruction manual, it requires focus, but a skilled builder can have it assembled on the table in a few hours.
That's a good way to look at it.
Setting up Trustchain, on the other hand, is like deciding to build a house. But first, you have to pour a massive concrete foundation, and you literally cannot do anything else for 4 days while you wait for the concrete to cure. Why would a city government with a limited IT budget choose the foundation that takes 4 days to cure?
It all comes down to the trade-offs inherent in decentralization. Why choose the concrete that takes days to cure? Because of the immovable permanence of the foundation it creates.
Okay.
Indy is faster to set up and, as we'll see, faster to operate. But it achieves that speed by sacrificing a degree of pure decentralization. It relies on trusted authorities. You have to inherently trust the consortium of universities and government departments running the Indy nodes.
And history tells us that trusting human institutions is eventually a vulnerability.
Exactly. Trustchain takes days to sync because it is refusing to trust any local human institution. It is anchoring your identity data to the Bitcoin blockchain, which is the most secure, immutable, globally distributed, and computationally powerful computing network in human history.
Wow.
With Trustchain, you don't trust a local consortium. You trust the cold, unfeeling laws of mathematics, secured by thousands of independent miners around the globe. For a city architect deciding on infrastructure, this is the ultimate dilemma. Do you prioritize the ease of deployment and efficiency of a permission system, or do you demand the uncompromising, trustless permanence of a public chain?
That is a fascinating architectural battle. So we know the tools,
Right.
we understand the engines powering the system, but how do these systems actually interact? When our hypothetical citizen is standing in the park holding their smartphone and they tap the button to check the local humidity, what actually happens in the digital space in the milliseconds after they tap the screen?
A lot happens very quickly.
The paper breaks down this architecture of trust into a very specific 4-stage workflow. I want to dissect this process step by step because this sequence is where the cryptographic theory actually becomes a functional smart city.
It is a beautifully elegant architecture. The entire workflow revolves around a central component called a proxy server, which functions as a REST API.
We used the bouncer analogy earlier. This REST API is essentially the bouncer standing at the velvet rope in front of the city's data vault. It handles all the communication between the decentralized world of the user's wallet and the centralized world of the city's physical sensor database.
Precisely. The citizen never touches the database directly. They only talk to the API bouncer.
Okay, so stage 1 of the workflow is presentation. The citizen opens the app and requests the data. The mobile app constructs a verifiable presentation, or a VP, and sends it to the API bouncer over a secure HTTPS connection. And because this is an SSI system, this presentation utilizes selective disclosure. The app looks at the bouncer's requirements and says, I will only send you the exact mathematical proof required to access this data and not a single bit of information more.
Right. The bouncer receives the proof. Now we move to stage 2, verification. The bouncer has to verify that the ID is real, that it hasn't been forged, and that it was issued by a trusted authority. And this is where the two engines diverge dramatically in how they operate.
Okay, let's look at Indy first.
If the city is running Hyperledger Indy, the API bouncer turns around and queries the permissioned Indy ledger. It checks the public decentralized identifiers and the schemas. But crucially, it has to interact with a specific entity called an endorser.
What is an endorser in this context?
In the closed-loop ecosystem of Indy, an endorser is one of those trusted nodes we discussed earlier. It is an authorized, vetted entity on the network, perhaps a server run by the municipal court, that has the specific cryptographic right to validate and record transactions on the ledger.
Got it.
The bouncer asks the endorser, is this mathematical signature valid according to the rules of our ledger? And the endorser replies with a definitive yes or no.
Okay, it relies on a trusted authority within the closed network. But what if the city is running the Trustchain engine?
The workflow shifts entirely. There is no central endorser to ask. Instead, the API bouncer queries the Trustchain and ION resolver. Its first job is to retrieve the user's public DID document from the decentralized network. Think of this as looking up the user's public lockbox.
Okay.
But then it has to perform a critical security check. It must ensure the credential hasn't been revoked. Let's say a citizen had their municipal access suspended. The credential on their phone might look mathematically valid, but its status has changed.
So how does it check that?
To check for revocation in a fully decentralized system, the bouncer queries something called IPFS.
I saw that acronym in the paper. IPFS stands for the Interplanetary File System, which sounds like something out of a science fiction novel. What is it really?
It is a remarkable technology. IPFS is a peer-to-peer network designed to create a distributed file system. On the normal internet, when you look for a file, you search by location, you point your browser to a specific server farm in Virginia owned by Amazon.
Right.
On IPFS, you don't search by location, you search by content. Every file is run through an algorithm that generates a unique mathematical fingerprint, a hash. The API bouncer asks the global IPFS network, who has the revocation list that matches this exact mathematical fingerprint? The network delivers the file, ensuring it hasn't been tampered with.
Wow.
Once the bouncer confirms via IPFS that the credential is not on the revoked list, it validates the cryptographic binding between the public key on the ledger and the private key that signed the request on the user's phone.
Yeah.
And it does all of this completely trustlessly, relying entirely on public infrastructure.
That is a staggering amount of computation happening in the background.
Yeah.
So if the bouncer is satisfied, the ID is mathematically real and not revoked, we move to stage 3, authorization. Just because your ID is valid doesn't mean you get to go anywhere in the club. The API checks the city's internal access policies. It asks, okay, you are a verified citizen of Santa Rosa, but does a standard citizen have the right, the role, or the scope to view this specific data set?
Exactly.
If you're requesting public humidity data, the answer is yes. If you're requesting the route access logs for the traffic grid, the answer is no.
Right. Role-based access control.
If you pass the authorization check, we reach the final step, stage 4, delivery. The API bouncer turns around, pulls the requested humidity data from the internal sensor database, packages it up, and securely delivers it back to the user's phone.
That entire four-stage flow presentation, verification, authorization, delivery must execute flawlessly every single time a citizen taps their screen.
And this brings us to the critical performance metrics the researchers gathered. Because it's one thing to design a perfectly secure, privacy-preserving cryptographic workflow. But human beings are notoriously impatient.
Yeah, very much so.
If it takes 5 minutes of standing on a sidewalk for the API to check IPFS and the Bitcoin blockchain, just so I can see the weather report, the socio-technical experiment has failed. People will just uninstall the app and go back to logging in with Google because Google takes half a second.
Exactly. Friction kills adoption. So the GCA team rigorously measured the latency of the systems. They looked at two primary metrics: creation time, which is how long it takes to establish a brand new digital identity on the ledger, and verification time, which is how long it takes to run that four-stage workflow for a returning user.
Let's look at the results. For creation time, Indy is incredibly fast. The paper shows that registering a new decentralized identifier on the permissioned Indy ledger takes an average of about 500 milliseconds.
It's half a second.
Half a second. That is perfectly acceptable for a user experience. But Trustchain. The data for Trustchain on creation time is wild. It has what I can only describe as a split personality.
It does, yeah.
The logical creation, the local generation of the cryptographic keys on the user's actual phone, is blazingly fast. It takes 50 to 300 milliseconds. However, for that identity to be permanently published and anchored into the public Bitcoin blockchain via ION, the process takes an average of 10 minutes, and it requires paying network transaction fees.
That's right.
Wait, 10 minutes?
Yes, on average, 10 minutes.
I have to stop right there. If I'm standing in the rain trying to unlock a smart city umbrella rental, or I'm at the municipal dump trying to open the automated gate, 10 minutes is an absolute eternity.
It feels like forever.
It's a non-starter. Does this latency mean that Bitcoin-anchored systems are just dead on arrival for the pace of daily civic life?
Your reaction is exactly why analyzing these metrics is so important, but it requires us to separate the immediate user experience from the back-end cryptographic finality.
Okay, explain that.
When you create an identity on Trustchain, the logical creation happens instantly on your device. You generate the public and private key pair. In theory, you can immediately begin using that key pair to generate off-chain cryptographic proofs. The local math works immediately.
Okay.
However, for that identity to be globally resolvable, meaning anyone in the world can look up your public DID without relying on an intermediary server, and for it to be permanently immutable, the transaction containing your identifier has to be batched by the ION network and permanently inscribed into a new block on the Bitcoin blockchain.
And that takes time.
By design, the global network of Bitcoin miners only solves the cryptographic puzzle to produce a new block roughly every 10 minutes.
Ah, I see. So the lock and key are instantly manufactured in my hands, and I can lock a box with them. But the rest of the world won't officially have the serial number of that lock recorded in the global registry for 10 minutes.
That is an excellent way to conceptualize it. And this massive disparity in latency highlights exactly why the researchers didn't just pick one system. It proves the absolute necessity of context-sensitive architectural design.
Right.
You would never use a Bitcoin-anchored system like Trustchain to generate a temporary single-use identity credential, say, a token just to unlock a rental bike for an hour. The latency and the transaction fees make it absurd. For rapid microinteractions, you use Hyperledger Indy, where the permission network gives you predictable half-second finality.
If you are establishing a foundational civic identity, a digital birth certificate, a master property deed, or a self-sovereign passport that you intend to use for the next 50 years, waiting 10 minutes to ensure that identity is mathematically indestructible, globally decentralized, and secured by the most powerful computing network on Earth is a completely trivial cost.
Precisely. It is about matching the tool to the task. Microinteractions require the fast, permissioned lane. Permanent, high-stakes credentials require the slow, indestructible public lane. A robust, smart city will likely require a hybrid architecture that utilizes both.
Okay, that makes sense. So that's the creation time. What about verification time? When our user already has their identity set up and they are standing in the park, running through stage 2 of the workflow, how long does the bouncer take to check the ID?
This is where the news is universally excellent. For read operations, simply verifying an existing mathematical proof, the system is highly efficient across the board. The paper's metrics show that the Indy workflow takes about 150 milliseconds to verify a credential.
Wow.
Trustchain takes slightly longer, between 50 and 300 milliseconds, depending on network conditions.
So a fraction of a second.
Yes. From the user's perspective, once the identity infrastructure is established, interacting with the smart city feels virtually instantaneous, regardless of whether the back end is permissioned or public.
And that instantaneous feel is critical, which brings us perfectly to the next major section of this research, because we've spent a lot of time talking about nodes and ledgers and zero-knowledge proofs.
We have.
We've established that the back-end plumbing is structurally sound. But the GCA researchers highlight a very pragmatic, unavoidable truth in their literature review. If the system is too hard for a normal human being to use, the cryptography does not matter. Citizens simply will not use it.
It is the great bottleneck of decentralized technology. The history of self-sovereign identity is littered with brilliant cryptographic projects that failed completely because of usability issues.
All right.
When you remove the central authority, when there is no forgot password button linked to Google or City Hall, the burden of security shifts entirely to the user. Complex cryptographic key management is terrifying for non-experts.
Yeah, I'd be terrified.
If you lose your private key in a poorly designed SSI system, you don't just lose access to an account. You permanently lose your digital identity. That is a massive, unreasonable cognitive load to place on an average citizen who just wants to check the bus schedule.
It's totally unreasonable. I mean, I can barely remember my streaming service passwords. If you tell me I have to securely manage a 24-word cryptographic seed phrase, write it down on a piece of steel and hide it in my floorboards just to prove I'm allowed to park my car downtown, I'm going to opt out.
Absolutely.
I will gladly hand my data back to Google for the convenience. And this is where the Santa Rosa pilot really shines. The researchers explicitly tackled this usability hurdle. They didn't hand the citizens of Santa Rosa a command line interface or a complex key generation tool.
No, they didn't.
They built a streamlined mobile app that actively, purposefully hides all of the intimidating technical details. The citizen just sees a clean interface with buttons that say request data, present credential, and approved. The app handles the generation of the zero-knowledge proofs entirely in the background.
And by doing so, the researchers emphasize that SSI cannot be viewed as a pure software engineering project. To succeed, it must be designed as a socio-technical system.
A socio-technical system?
Yes. It means the technology must be deeply integrated with human psychology and societal habits. It must balance hardcore cryptographic security with social acceptance, intuitive design, and regulatory compliance. The system must adapt to human behavior rather than demanding that humans adapt to cryptographic architecture.
And the paper highlights some brilliant design choices that protect the human user behind the scenes without them ever knowing it. For example, the use of pairwise DDs. I want to unpack this because this is another superpower of the architecture. What exactly is a pairwise DD and how does it protect the user?
To understand pairwise DDs, consider how you operate in the physical world. You have one social security number or one national ID number. If you give that same exact number to the library, to the tax office, to the transit authority, and to your employer, it creates a massive privacy risk. Because if those entities ever decide to collude, or if a data broker buys information from all of them, they can use that single static identifier to correlate your data across completely different domains, mapping your entire life.
Right, the identifier acts as the thread that ties all the separate databases together.
Exactly. A pairwise DD system destroys that thread. Instead of having one master digital identifier, your SSI wallet automatically generates a unique, mathematically separate identifier for every single relationship you establish.
Wow.
When you connect with the municipal library, your wallet generates ID number A. When you connect with the transit authority, your wallet generates ID number B. They are both mathematically tied to your private key, but they look like completely unrelated strings of gibberish to the outside world.
That's incredible.
The library and the transit authority cannot correlate your data because they don't know they are interacting with the same person. It drastically strengthens privacy by preventing cross-domain tracking.
That is brilliant. It's like wearing a mathematically perfect disguise to every single building you enter. The paper also mentions mechanisms for cryptographic key rotation and recovery, ensuring that if you do drop your phone in a lake, your digital civic life isn't permanently destroyed. The app can split recovery codes among trusted contacts or securely back up encrypted versions.
Yeah, that's a huge part of the socio-technical approach.
This entire approach really reminds me of the early days of the internet. Back in the early 90s, if you wanted to send an email or view a web page, you had to know command line code. You had to understand how TCP/IP protocols routed packets across servers. It was a highly technical project reserved for computer scientists.
It was.
Now, we just tap a colorful envelope icon on a piece of glass, and the magic happens instantly. Are the researchers essentially suggesting that a well-designed mobile digital wallet is the browser for the self-sovereign identity era? Is the wallet the interface layer that finally abstracts away the terrifying complexity and makes this accessible to, say, my grandmother?
That is a phenomenal, highly accurate analogy. Yes, enthusiastically, yes. The wallet is the browser. If a user has to understand what an IPFS hash is or how an ION resolver interacts with the Bitcoin blockchain in order to access their municipal services, the system has fundamentally failed as a public utility.
Absolutely.
The true brilliance of the Santa Rosa pilot isn't just proving the cryptography works. It's proving that enterprise-grade, zero-knowledge, Bitcoin-anchored cryptography can be successfully wrapped in an interface as friendly, intuitive, and frankly, as boring as a local weather app. When the infrastructure becomes completely invisible to the user, that is the exact moment when mass adoption becomes possible.
When the infrastructure becomes invisible, that is exactly what we need. So the pilot in Santa Rosa was a documented success. They proved the decentralized plumbing works, they proved the cryptographic latency is manageable, and they proved the socio-technical interface can be user-friendly.
They checked all the boxes.
But it was, ultimately, just a pilot in one municipality. What are the GCA researchers planning to do next? Where does this technology go from here?
Well, the conclusion of the paper doesn't treat the pilot as a finish line, it treats it as a baseline. They outline a very ambitious roadmap for future work.
Okay, what's on the roadmap?
First, they plan to evaluate the architecture's performance in significantly larger scale scenarios. Testing it with a few users, checking humidity is one thing. They want to measure the latencies in DID resolution and distributed artifact retrieval when tens of thousands of citizens are hitting the network simultaneously during a peak event.
Right. Stress testing the system. Making sure the API bouncer doesn't get overwhelmed and crash the server when the entire city tries to check the transit schedule during a snowstorm.
Exactly. Scale introduces entirely new friction points. Secondly, they plan to conduct extensive qualitative usability studies with highly diverse citizen profiles. They need to assess the actual human experience of these digital wallets across different demographics.
Makes sense.
Does the interface make sense to the elderly? Does it work for non-native speakers or individuals with visual impairments? Is the complex flow of credential presentation truly intuitive?
Because, as we established, a socio-technical system has to work for the whole society, not just the early adopters.
Right. Third, they want to integrate this authentication pipeline with other urban services beyond environmental data, connecting the SSI wallet to municipal transit systems, healthcare portals, or even local voting mechanisms will provide real-world operational data to assess the true feasibility of completely replacing centralized logins in a production environment.
That would be a huge step.
It would. And finally, they want to investigate advanced mechanisms for operational resilience. Crucially, they highlight an urgent need to examine the impact of emerging technologies on this architecture. Specifically, the need to integrate quantum-resistant cryptographic approaches.
Okay, hold on. I have to hit the brakes here. Quantum resistance.
Yep.
We have spent this entire deep dive establishing how hard it is to just get a normal person to use an app to securely check a humidity sensor without feeding their data to a tech monopoly. The pilot just barely proved that the basic app interface works. And the researchers are already worrying about theoretical quantum computers breaking the blockchain at some point in the distant future. Isn't that jumping the gun? Let's solve today's problems before we start engineering for science fiction.
I completely understand that reaction. It sounds like over-engineering. But what is absolutely vital to understand about the realm of cryptography and digital identity is that foresight is not a luxury. It is mathematically non-negotiable. If we are building the foundational digital infrastructure that will hold our civic identities, our medical records, our property deeds, and our financial histories for the next 50 years, we absolutely have to anticipate the hardware capabilities of the adversaries of the future.
I hear that, but why can't we just upgrade the system later? I mean, if a working quantum computer is 30 years away and we think it might break the encryption in 2056, why don't we just issue a software update to the digital wallets in 2055?
Because of a deeply concerning threat vector recognized by the intelligence and cryptographic communities, known as Harvest Now, Decrypt Later.
Harvest now, decrypt later. Okay, what does that actually mean?
To understand the threat, we have to look briefly at how the cryptography securing these systems, like the Hyperledger Indy network or the Bitcoin blockchain, actually works today. They rely on what is called asymmetric encryption, specifically algorithms like elliptic curve cryptography or RSA. At a very high level, this encryption relies on mathematical trapdoors. It is incredibly easy for a standard computer to multiply two massive prime numbers together to get a gigantic result. But it is practically impossible for a standard computer to look at that massive result and figure out which two specific prime numbers created it.
Right, the trapdoor only goes one way.
Exactly. That mathematical difficulty is the lock on your digital vault. It would take a supercomputer millions of years of guessing to break it.
Okay, so our data is safe.
It is safe from classical computers. But a quantum computer operates on entirely different principles of physics. Using algorithms like Shor's algorithm, a sufficiently powerful quantum computer doesn't have to guess one by one. It uses quantum states to find the prime factors exponentially faster.
Oh, wow.
What takes a classical computer millions of years could theoretically take a quantum computer a few hours.
Wow. Okay, so when that machine turns on, the locks break. But what does that have to do with harvesting data today?
Malicious actors, state-sponsored hacking groups, intelligence agencies, massive cyber syndicates. They know that quantum computers are coming. So today, they are executing massive data scraping operations across the internet.
Wait, really?
Yes, they are intercepting and storing vast amounts of heavily encrypted data that they cannot read right now. They are just hoarding the ciphertext in massive server farms. They are waiting for the day when quantum computing reaches sufficient power. When that day comes, they will take the data they harvested today, run it through the quantum computer, and crack it open.
Oh my God.
If your permanent self-sovereign identity was anchored using cryptography that is vulnerable to quantum algorithms, then harvest now, decrypt later means that everything you do today, every credential you present, every health record you verify, every civic action you take, could retroactively become entirely public in 15 years.
That is wow.
Therefore, building quantum resistance into the foundational mathematical layer of self-sovereign identity from day one is not jumping the gun. It is the absolute minimum requirement for ethical defensive systems engineering.
Harvest now, decrypt later. That is absolutely chilling. But it perfectly illustrates exactly why the GCA's research is so vital and why they are thinking decades ahead. We aren't just building a new login button. We are quite literally pouring the concrete for the vault that will protect the digital futures of entire societies. And we have to make sure the walls are thick enough to withstand weapons that haven't even been fully invented yet.
That's exactly it.
Let's summarize the incredible journey we've been on today. We started by looking at the insidious danger of the big tech data trap within our modern smart cities. How our desire for frictionless convenience has slowly turned us into exploitable data points for massive advertising monopolies.
Right.
We explore the intricate mechanics of decentralized and self-sovereign identity, learning how decentralized identifiers and verifiable credentials allow us to prove who we are without ever revealing our underlying secrets, utilizing the cryptographic magic of zero-knowledge proofs and selective disclosure.
The glowing green card.
Exactly. We saw how the GCA researchers took this complex theory and dragged it into the real world, testing it in the Municipality of Santa Rosa. We watched them run a high-stakes tech bake-off between the fast, closed-loop efficiency of the permissioned Hyperledger Indy and the slow, immutably secure, universally public permanence of the Bitcoin-anchored Trustchain.
It was a fascinating comparison.
And finally, we learned that to truly empower citizens, this entire formidable cryptographic architecture has to be completely hidden behind a simple, friendly mobile app, creating a socio-technical system that respects human behavior while defending against future quantum threats.
Yes.
I want to remind everyone listening that the battle for your digital privacy isn't just happening in dramatic Supreme Court rulings or in closed-door boardrooms in Silicon Valley. It is being fought right now, block by block, by researchers at universities like Unijuice and URI who are writing the code and running the pilot projects designed to pry the master keys out of the hands of centralized tech giants and put them directly back into yours.
It is a profound and necessary shift in the architecture of power. But I think it's important to recognize that it also comes with profound responsibility.
How do you mean?
If these systems scale the way the researchers hope they will, and the way society likely needs them to, your entire life will eventually be stored in a perfectly secure, self-sovereign digital wallet. Your education records, your civic rights, your property deeds, your most sensitive health records.
Right.
Which raises a lingering, perhaps uncomfortable question. What happens when we lose our physical devices and fail to secure our backups? Or, looking even further ahead, what happens when our digital identities outlive our physical selves?
Oh, wow.
In a future where big tech no longer holds the master key to reset our passwords and the government can no longer access our encrypted histories, we become our own absolute authority. But in a world without safety nets, are we truly ready for the unforgiving, absolute responsibility of being our own sovereign?
That is a heavy, necessary thought to leave on. As we demand to take back control of our digital lives, we have to be prepared to carry the full weight of that control. Thank you so much for joining us on this deep dive into the GCA's groundbreaking research. It has been an absolute privilege to unpack this architecture with you. Keep questioning the systems around you, keep fiercely guarding your data, and we will catch you on the next deep dive. Keep exploring.